For decades, the solar industry has been pushing standard blue silicon panels as hard as the laws of physics allow. But physics has a strict speed limit. For a standard silicon cell, the absolute maximum amount of sunlight it can convert into electricity is capped at exactly 29.5%. Recently, researchers started engineering a completely different class of materials called perovskites. Perovskites are a family of synthetic crystals that can be precisely tuned to absorb specific wavelengths of light that silicon misses. Breaking this 29.5% limit changes the math for renewable energy. It represents a transition from decades of incremental updates to a single substantial leap in what a single panel can produce from the exact same footprint. This diagram shows how engineers are combining the two materials into a tandem cell configuration. Manufacturers layer a specialized perovskite crystal directly on top of a traditional silicon base. The perovskite catches high-energy light, while lower-energy light passes through to the silicon underneath. By stacking these materials, researchers recently pushed tandem solar cells to a record 34% efficiency in controlled laboratory environments. And this is moving out of the lab right now. Companies like Oxford PV are actively manufacturing commercial tandem panels and have already signed major patent licensing agreements to deploy this technology across the U.S. market. The commercial momentum is aggressive, with manufacturers rushing to scale production. But there is a severe problem hiding inside the crystal lattice itself, one that threatens to derail the entire global rollout. Perovskites use three components, A, B, and X, in a tight cubic structure. The Goldsmith factor predicts if atoms lock into this active black phase. But as temperatures shift, atoms expand. This precise fit means slight changes warp the cube into useless hexagonal or orthorhombic shapes. Outdoors, a solar panel bakes in the sun and cools at night. Under these normal operating conditions, some of the highest efficiency perovskite blends warp over a matter of days or weeks, degrading into a useless, non-conductive state known as the yellow delta phase. Material scientists are currently testing thousands of different chemical alloys to force the crystal to stay locked in its cubic shape, regardless of the weather. We'll be covering those engineering breakthroughs as they happen, so make sure you're subscribed to follow the progress. The exact feature that makes perovskites so powerful, the ability to swap out different atoms to catch different colors of light, creates an inherently fragile lattice that actively wants to pull itself apart. Right now, the most effective atom for the center of that cubic structure, the anchor holding the highest efficiency panels together, is lead. Deploying millions of lead-based panels across residential rooftops creates a major environmental liability. If the glass cracks in a hailstorm, rain washes through the panel, and that heavy metal easily leaches directly into local soil and water systems. This chart shows the efficiency gap between perovskite materials. When engineers replace toxic lead with a safer periodic neighbor like tin, performance plummets. Lead-based cells easily clear 20%, but the highest certified efficiency for a lead-free tin device sits at exactly 9.6%. The industry is currently trapped in a tight compromise. They can manufacture a panel that is chemically safe, but too inefficient to sell, or they can deploy the high-performance cells that depend on toxic heavy metals to function. To significantly cut global carbon dioxide emissions by 2050, the world needs to install more than 20 terawatts of total solar capacity. Reaching that number requires scaling up manufacturing and deployment faster than we ever have before. Because they extract so much more power from the exact same surface area, perovskite silicon tandems represent the most direct mathematical route to hitting that 20 terawatt target without requiring double the land. But to offset the cost of manufacturing and make economic sense for utility companies, these panels cannot fail after a few months. A commercial solar installation needs to survive roughly 30 years of continuous rain, hail, and intense heat. What we are watching right now is an aggressive live engineering sprint. Researchers are racing to develop advanced encapsulants to seal the lead inside, while simultaneously tweaking the crystal chemistry to lock the structure against temperature swings. We possess the chemical blueprint for a highly efficient solar panel. The remaining challenge is entirely structural. If materials scientists can solve the crystal's molecular fragility, we can scale this energy source globally. If they can't, the theoretical efficiency won't matter.